So now that we've had some experience with working with the radian measure, we're going to talk about how we can find the length of an arc and the area of a sector of circles. Okay, and this section is mainly going to be dealing with circles. So there's a few other ideas that have to do with traveling around the circle, which we'll get to. But before we do that, let's first define what an arc length is. And this is kind of very straightforward to figure out because we're going to use our idea about the radian measure to help us find the arc length. So when we say arc length, by definition, this is the distance around a part of a circle. Okay, and we could easily find that because we could use the idea in section 3.1. So we can say that, notice that in 3-1 we found that the angle measure of radians around a circle was found by the quotient of the arc length created by theta and the radius of the circle. So if you remember in section 1 we said theta is equal to S over R, where S is the arc length. So literally grabbing this equation and solving for S, that'll give us the arc length. So thus the arc length of a circle is found by S equals to R times theta. And that's literally, we just grab this equation, multiply both sides by R, and we got this. But remember, one comment I want to make is what? Theta must be in radian measure. So if it's not a radian measure and you use this formula, you're going to get an incorrect solution. Okay, so make sure that theta is in radian measure. Okay, so for example 1, we'll say if a circle has a radius of 5 centimeters, what is the length of the arc subtended by an angle of 1.2 radians. Now, one other comment I want to make is, before we do this example, I kind of forgot to mention this up here. Theta is, remember, what is theta? This is also not only does it have to be in radian measure, but theta is the central angle of the circle. So, in other words, if I had to draw a visual off to the side here, if let's say I want to know what this arc length is, let's say this is the part of the circle that I care for, to find that arc length, I would need to find that theta, which that theta is in radians, and that's my central angle, and this is the radius. Okay, so whenever we say, so if I come back down to example 1, if I were to draw a picture for this, literally what we're saying is we have the circle, the central angle is 1.2 radians, which ends up being something like this, that's 1.2 radians, and then we're told that the radius is 5. So we didn't necessarily need a picture for this, in all honesty, because we were given all the information we need. So my arc length would just literally be what? 5 times 1.2, which ends up being 6 centimeters. So this length that we're talking about is 6 centimeters. Okay, so that's all we're going to talk about as far as the arc length goes. So now let's talk about something that's very important, and it shows up quite a bit in calculus as well, which has to do with angular and linear speed. Okay, so in fact they're tied together. So let me first define what linear speed and angular speed is, and then we'll talk about how to find linear and angular speed. Okay, so linear speed is defined as the rate in which an object moves around a circle. So what I'm trying to tell you is basically anytime you see angular and linear speed, think about an object moving around a circle. So the linear speed is the rate of the object, or the actual speed of the object. So for example, think about it this way. If I'm running around a circular track, let's say, and I'm running at 5 miles per hour, then my speed is 5 miles per hour, which is what my linear speed is. So it's basically this object that's running around this, or moving around the circle, which is just literally the speed of that point that's moving around the circle. That's what the linear speed is. Okay, so you might be wondering, well, why is it that we're talking about moving around circles? You'll see the connection in a minute. But when you hear the word linear speed, it's just literally, hey, how fast is this object moving around the circle? And that's what it is. And if you think about it, in classes before this, you have talked about how to find the rate of an object, which is the whole idea is rate is equal to what? Distance over time. If you guys remember the distance equals to rate times time equation, this is one of those classic equations, which means what? The rate is distance over time. And in all honesty, the idea used here is similar to, or it's not similar, it is just that idea. Okay, now let's talk about what angular speed is, and then we'll kind of connect them together. Okay, so angular speed is defined as, so this is the rate in which the central angle changes as the object moves around a circle. Okay, so notice how angular speed has to do with what? And the name itself should tell you. It's the speed, or it's the rate in which the angle changes. So if you think about it, like let's draw this again. Let's pretend that the object is here, and the object travels at a certain speed. And what are you noticing? As this object travels around the circle, what's happening to this theta, or that angle? That angle is also changing, right? And as this point moves around at a specific speed, this angle itself is changing at a specific speed. Now hopefully you're starting to see a connection between this point moving around and the speed of the angle changing. Obviously the faster this point moves, the faster that angle changes. The slower this point moves, the slower this angle changes, right? Because think of it this way. Imagine you're standing here and you're just kind of measuring the angle that's changing as this guy moves around the circle. So as this point moves around the circle, we want to know how much is this angle changing by and how fast. And that's what our angular speed is. Okay, so let's now let me give you the formulas of finding linear speed and angular speed. And remember how I said the rate is equal to distance over time? I promise you it's literally using that equation, right? So if you've heard of this equation, which you should have, that's literally what we were using. So finding linear velocity. So if you think about it, as I mentioned earlier, so let me write this out again. Rate is equal to distance over time. Okay, so the speed of an object is equal to the distances traveled divided by the amount of time elapsed. So for linear speed, we're going to call it v because it's the velocity of the object. So that's what we're going to call. So it's v for the linear velocity is equal to, now if you think about it, if I tell you, hey, how fast is this point moving? Let's say if I draw this out again, how fast is this point moving? If I give you from here to here information from the point going from here to here, can you tell me how fast the point is moving? Well, you'd first say I would need to know the distance is traveled, which if you think about it, this distance is what? It's a part of the circle, which we just talked about. That's the arc length. So instead of distance, we're going to say S, because when we're talking around about the distance around the circle, that's the arc length, divided by, well, how long did it take for it to travel this distance, which is the t. So as mentioned, notice how this equation, that equation are literally the same, except now instead of the distance, or the distance is being described as the distance around the arc length. So that's the linear speed, which would give you the actual speed of this object moving around the circle. Now, as far as angular velocity is concerned, now we want to know how fast the angle is changing. So with angular velocity, if you think about it, we're going to have the following. We're going to use omega, which this is just a Greek letter. So this means our angular speed is equal to, now instead of talking about, hey, what distance has this object traveled, to find out how fast the angle is changing, we want to know from this point to this point, what's the total angle that it has traveled, which instead of distance now we care about the angle, which would be theta, over, and how long did it take for it to go a length of this, or a measure of that angle, which is t. So this is telling you how fast the angle is changing. So notice once again it's following that same equation that I gave you earlier, except this is now saying instead of the distance, it's what angle has it covered divided by how long it took for it to cover that angle. And anytime you grab some kind of a length or measure of something and you divide it by time, you're finding its speed. Now why is this angular speed? Because we're trying to figure out what angle is changing for that, or at how fast this angle is changing for that unit of time, whereas this is telling you what distance is it traveling for that unit of time, which this gives you the speed of the object, this gives you the speed of the angle. Okay, so these are the two main equations. Now, as I mentioned earlier, if you notice, as the point moves around the circle, if it moves faster, not only is its linear speed increasing, but its angular speed is increasing as well, right? Because if I travel faster, then this middle angle is changing faster. If I slow down, the center angle, or the central angle, the rate in which it's changing, it also slows down. So what I'm trying to show you is, notice how there's a connection between linear and angular speed. So there is a relationship, and I'll show you guys how we can use that relationship to connect linear and angular speed to each other. So in other words, what I'm telling you is, hey, if you know what the linear speed of the object is, you could probably use that information to find the angular speed. So let's connect these two. So we could say that, notice that there is a relationship between linear and angular velocity. That is, if an object if an object's linear speed increases, so does its angular velocity. So if one affects the other, what we're trying to say is we can write or we can make a connection between these two equations, and that's exactly what I'm going to do right now. So notice how, let's start off with one of these. Let's start off with linear velocity. So if I start off with linear velocity, so if we have v, so somehow I'm going to connect this to omega. So if v, by definition, what is it that we said, is defined as s over t. And if you remember earlier, we said, hey, the arc length is defined as r theta. So I could say this is the same thing as r theta over t, right? Because earlier we said s equals to r times theta. And then notice how if I factor out a theta over t, I get what? Theta over t times r. So all I did was actually I factored out the r and I left theta over t. Now why did I do that? Because notice what theta over t is. Theta over t is my angular velocity, and that means what do I get? Theta over t is omega r. And notice how we made the connection. So what does this imply? Linear velocity equals to the angular velocity times the radius. So that's another equation that we can use when it comes to angular velocity and linear speed. So any one of these three, they're all good and good to go, but just make sure you know all three of those. So let's do an example where we'll put angular speed and linear speed to use. And remember, these have to do with points traveling around a circle or objects traveling around a circle. So for example 2, we'll say point P travels around a circle of radius 15 feet. Find the linear velocity if its angular velocity is omega equals to 12 radians per minute. Okay, so if you notice this, the good news here is that we have the angular velocity, and if you remember, we're asked to find the linear velocity, and we show that there's a relationship between linear and angular velocity. So what I'm going to use, I'm going to choose to use v equals to r omega, because we're asked to find the linear velocity. Now we have the angular velocity and we have the radius. So that just makes this very straightforward, because we have 15 feet was the radius times 12 radians per minute. And of course, once we multiply that out, we get 180 feet per minute, right? Because this had a measure of 15 and the unit of time on the angular velocity was in minutes. Okay, so let's go on to the area of a circle, and then we'll come back to this. We'll do one more example, and then that will on this angular and linear speed. But before we do that, I want to talk about the area of a circular sector. So we're now gonna basically say, okay, we're gonna find the area of a circle. So if theta is a central angle in a circle of radius r, the area of the sector formed is a equals to 1/2 r squared theta, with theta in radians. Okay, now if you recall, you have worked with areas of circles. Now this is a part, so when you see a circular sector, we're saying it's a part of a circle. So for example, if I have a circle and this is my central angle theta, well, and I know the radius of the circle, well, then I could find the area of that piece of the pie, which is 1/2 r squared theta. Now, to be honest with you, you've seen this formula probably in a different form, so this might not look familiar to you, but I promise you this is using the whole idea of pi r squared, because see, we know that the area of an entire circle is what? Is pi r squared, right? But that's the whole circle. So if you at some point in one of your courses you may have said, or you may have seen, well, if I want a part of the circle, what do I need to figure out? I need to figure out how much of the circle is this. Now, if you think about it, the whole circle represents has a central angle of 360 degrees. So if I want just this part, that would be what? I want just the theta over the 360 degrees. Except the only problem here is what? Now that you see this is in degrees, we're assuming that theta is in what? Degrees. Except this formula is saying what? Theta is in radians. So what I'm claiming to you is what? That this equation is literally the same as that equation. The only difference is this is in degrees, and hopefully you understand why this is taking only what? That part of the circle, right? Because it's only theta of the whole 360, okay? But I promise you that if we grab this and we convert theta in terms of radians, we'll get literally just that. And why don't we do that? So if you think back to the last section, how do we convert theta over 360 degrees into radian measure? We would have to multiply it by what? It would be 360 degrees, because we want the degrees to cancel out, don't we? Over pi. Right, so I'm just trying to get rid of the 360. Now notice what happens here. Oh, not 360, sorry, this should be 180, right? Because remember our conversion was 180. So look at what happens here now. The pi's cancel out, the 360 and the 180 cancel out, that becomes a 1, that becomes a 2, and look at what we just have. We're left with r squared theta 1, so it becomes 1 r squared theta, and then what's on the bottom? Just a 2. Which that's literally that equation. So just keep that in mind. So let's look at our third example where we'll be finding areas of sectors. And in all honesty, these are equations that you just need to make sure you memorize, because if I do ask these on the exam, which I probably will to some extent, you're just going to have to use the formulas to be able to get through this anyway. So the next question is, what is the area of a circle or circular sector formed by a central angle of 3 pi over 4 if the radius is 22 feet. So once again, this should be very straightforward. We have the radius, we have the central angle, and that's already in radians. So the formula for this is just 1/2 r squared, which is 22 squared, times 3 pi over 4. So the rest of this is just simplifying things out. So 22 squared gives us 484, and if so this becomes 484. If I divide that by 2, I get 242 times 3 pi over 4, and it looks like 242 can be divided by 2. So what do we get if I divide this by 2? That becomes 121, that becomes 2. So we get 121 times 3, which is 363 pi over 2, and there's my answer. And I'm going to leave it as exact, and this is in feet squared, right, because we're talking about area. Okay, so now the last example I want to do, which will go back to our linear speed and angular speed, which this is an interesting one, and it's something that hopefully will make sense when we talk about it. So the wheels of a racing bike have a radius of 13 inches. How fast is the cyclist traveling in miles per hour? If the wheels are turning at 300 rotations or revolutions per minute. Okay, so this is actually, we have to be careful with this now. See, revolutions per minute, this is telling us how fast the tire is turning, right? Which the revolutions, this can give me the angular speed. So by revolutions per minute, see, here's what we know. One revolution is equal to what? 2 pi radians. So if I could write this in radians per minute, that's angular speed, because remember, angular speed was theta over time, which that we can do. So if I grab the 300 revolutions per minute, I could change this to radians per minute, which then that would be my angular speed. And how do I do that? Well, I know that to convert this from revolutions to radians, I need to cancel out the revolutions, which the revolutions right now are on top. So this revolution is going to go to the bottom. So one revolution is 2 pi radians. So if I do that, I get what? I get 600 pi radians per minute, which this is my angular speed. Now look, when a tire turns, it has an angular speed, right? Now, the linear speed of the tire, which is how fast the point is moving around this circle, will actually cause the bike, if this is the bike, the linear speed of this tire is actually going to give you the speed of the bike, which notice how it gets the name linear speed, because if this spins, the bike moves in a line, and how fast is the bike moving is the same as the linear speed of the object moving around the circle, around this tire. So in other words, since I have the angular speed, I could use the angular speed to find the linear speed of the tire, which would then give you the actual speed of the biker. So that we know how to do, because we earlier on found out that V equals to R omega, which that's my linear speed, that's the angular speed, and we have the angular speed because remember that's in radians per minute. So my linear speed now becomes the radius, which is what? 13 inches of the tire, right? It's 13 inches. And its angular speed is 600 pi, which 13 times 600 becomes 7,800 pi, and this is in what? Inches per minute. Okay, now the rest of this is all supposed to be conversions, because what are we asked to find? In miles per hour. Now one comment I want to make is that 1 mile is equal to 5,280 feet. So we're going to need that conversion, and we're going to use our calculator here. So I want to write the 7,800 pi, and I'm going to probably multiply the pi out towards the end just to get this to be in terms of miles per hour like a whole number. So we'll round to the nearest whole number. So this is in what? Inches per minute. So I want to change this what? Let's change the inches to miles first. So what do I know? I could change inches to feet, because what do I know? 12 inches is 1 foot. So that'll cancel the inches. Now I'll be in feet, except we want it in miles. And what did we just say? 5,280 feet is 1 mile. Okay, so now I've changed the inches to miles. Now I need to change the minutes into hours, which that's not difficult, because now what do I know? The minutes is on the bottom, so to cancel it out, I need 60 minutes is 1 hour. So this might look a little messy, but what I did is I just wanted to convert this all in terms of miles per hour, because the inches cancel out here, then the feet cancel out here, and then what am I left with? I'm left with miles, and then the minutes cancel out here, and I'm left with hours, so it'll be miles per hour, and that's what we wanted. So now I could use my calculator to multiply this out. So I'm going to say 7,800 times pi times 60. So I'm multiplying all the top parts out, and then I'm going to divide by what? By 12, and then I'm also going to divide by 5,280, which then that gives me about 23.2 miles per hour. Okay, so that's pretty much this is kind of probably as most involved as these linear speed and angular speed are going to get, right? So that takes care of this section. As always, if you have questions, don't hesitate to email me.